Hi, my name is Jørgen Svendby, and on behalf of my colleagues at Prototech, I'm going to present our contribution with the title The Use of Additive Manufactured Inconel 625 as Bipolar Plate for the High Temperature Proton Electrolyte Membrane Fuel Cell. I'm first going to explain how a fuel cell operates, and I'm going to use a single cell as an example. The single cell comprises of an anode side and a cathode side. On the anode side, you supply the fuel, which in case of high temperature PEM fuel cell is hydrogen gas, and on the cathode side, you supply an oxidant, which is either pure oxygen or air. These two species are transported through the engraved flow channels on the bipolar plates. Then they are homogeneously distributed by the carbon cloth and the gas diffusion layers over the catalyst layers. On the anode side, hydrogen gas is oxidized to positive ions and electrons. These electrons go through an external circuit to power whatever unit you want to power, while the positive ions flows from the anode to the cathode through the membrane. On the cathode side, oxygen gas is reduced in the reaction with the ions and the electrons, forming water. So the overall reaction is consumption of hydrogen gas, oxygen gas into water, heat and electricity. In addition, the exhausts from both the anode and the cathode sides have to be transported out by the bipolar plates, and especially on the cathode side where you have water. To achieve high power, you have to stack the single cells on top of each other, creating a so-called fuel cell stack. The fuel cell stack comprises of end plates at the very ends, and then you have the single stack that I just described on the previous slide. So each single cell have two bipolar plates on the anode and the cathode side. Then you have sealants, and then you have the so-called membrane electrode assembly in the middle, which comprises of the membrane and then two catalyst layers and two GDL layers. Bipolar plates have numerous functions in a fuel cell stack. They separate each cell from another in the stack, as you could see on the previous slide. They supply fuel and oxygen to the cell and removes exhaust products using the flow channels. They conduct current through the stack, and they function as heat provider, heat sink of the stack, normally using a liquid coolant that passes through internal flow channels of the bipolar plates. The bipolar plates contributes largely to the total stack weight, volume and total costs. And as you can see here, for a 80 kilowatt PEM fuel cell stack calculation, almost a quarter of the total costs are due to bipolar plates. Changing from the state-of-the-art graphitic composite material to metal can reduce all three of these parameters, and using additive manufacturing might lower the cost due to its potential of producing challenging geometries. The challenge of using metallic bipolar plates is corrosion. In a high-temperature PEM fuel cell, there is a presence of concentrated phosphoric acid in its membrane, and in combination with an operational temperature of 120 to 200 degrees C creates a highly corrosive environment. In addition, the resistance towards current flow between the bipolar plate and the gas diffusion layer, known as interfacial contact resistance or ICAR, tends to increase during operation due to the formation of a passivating layer on the bipolar plate surface. It's therefore important to test the corrosion properties and measure the ICR of samples intended to be used as bipolar plates. We have therefore manufactured Inconel 625 metallic samples using additive manufacturing and tested their corrosion properties. In addition, we have measured the ICR before and after the corrosion tests. We have obtained scanning electron microscopy images for analysis before and after the corrosion tests, and we have compared this with commercially purchased Inconel 625 metal samples. For the additive manufacturing process, we used the DMG Mori LaserTech 30 system, and here you can see an illustration of how the production was done. You have the argon gas flow in here, and you have the recoater direction this way, and here you have the metal samples. The laser thickness was 50 micrometer. During the hatching, the laser speed was 0.3 meter per second and 140 watt power was used. During the contouring, 1 meter per second laser speed was used and 254 watt was the power of the laser. After production, the samples were machined to an arithmetic roughness average of 0.3 micrometer. Forged commercial samples were purchased from VDM Metals and they were machined to a similar RA value. The corrosion electrochemical measurements were conducted in a flex cell made of PTFE that we purchased from Gascatel. In this cell you have the so-called 3 electrode setup, where the sample is known as the working electrode. You have a reference electrode that was a Hydroflex reversible hydrogen electrode from Gascatel, and a counter electrode which was a built-in iridium platinum alloy. The measured current was between the working electrode and the counter electrode, and the measured potential was between the working electrode and the reference electrode, creating a much more accurate potential value. The electrolyte used in this experiment was concentrated phosphoric acid purchased from VWR, and we heated up the cell to 150 degrees C. One of the experiments we conducted was so-called Chrom Perimetry, where we measured the current while holding the sample potential constant of a value of 0.65 volt versus the reference electrode for 24 hours. In the literature, it's reported that the cathode in a high-temperature PEM fuel cell during normal operation experiences this voltage. The current here is normalized by the surface that was exposed to the electrolyte, in this case 3 square centimeters. As you can see here, the current density of the additive manufactured sample is always higher than the commercial sample. This indicates a higher corrosion of the additive manufactured sample, since we can assume that there is a direct correlation between the current and the corrosion rate. Another experiment we conducted was so-called linear sweep voltammetry, where we changed the potential at a constant rate of 1 millivolt per second, starting at a value of minus 0.3 volt versus the reference electrode, going all the way to a value of roughly 1.4 volt. As you can see here, there's a dip in the plot indicating where the corrosion potential is. To the left of the corrosion potential, then you have a reduction reaction on the sample, which can be everything from metal deposition to oxygen reduction reaction. To the right here, you have oxidation or corrosion of the sample primarily. You have a peak here, which is believed to be due to the formation of a passive film created on the surface of the sample. This passive film normally keeps the corrosion rate at bay, making sure that the current is primarily constant in this area here. But then when you reach a certain potential, this protective layer tends to crack up, and then you have a rapid increase in the corrosion rate. In addition, to be able to obtain the corrosion potential from this dip, you can also obtain the corrosion current density. As illustrated from this image here, you draw 2 straight lines in this manner, and where they cross, you can read off your corrosion current density. For our commercial sample, the corrosion potential was measured to be minus 65.9 millivolts, while for the additive manufactured it was minus 61.5 millivolts. Since both samples are Inconel 625, we are not surprised that they are relatively close to each other. For the corrosion current density, the commercial had a value of 160 microamps per square centimeter, while the additive manufactured had a value of almost twice as much, 300 microamps per square centimeter. This can be directly translated into so-called corrosion penetration rates, where you have for the commercial a value of between 0.94 to 2.7, while for the additive is 1.7 to roughly 5. This is in correlation with the Chrom Perimetry measurements that we also did. Here's an overview of the device that we use to measure the interfacial contact resistance. You place the sample between 2 GDLs and then you sandwich them between 2 gold-coated copper plates. You apply a force and then you supply a constant current, which in our case was 1 amp. Then you measure the voltage with a voltmeter. Then you also do this for only 1 GDL sheet. From Ohm's law, you can calculate the resistance from the measured voltage and the applied current. Some mathematical assumption needs to be done to obtain the interfacial contact resistance between the GDL and the sample seen here. For this configuration here, you measure a total resistance comprising of the interfacial contact resistance between the GDL and the gold-coated copper, between the interfacial contact resistance of the GDL and sample, the resistance through the gold-coated copper, the GDL and the sample. For this configuration with only one GDL sheet, you get a total resistance here, shown here. By assuming the resistance through the sample, the GDL, and also through the gold-coated copper is 0, and then adding one equation to another, then you end up with this equation. A pressure of 140 Newton per square centimeter was applied on the samples. This is due to the reports in the literature that this value is common for PEM fuel cell stacks. As you can clearly see, the ICR value for the commercial sample is higher than the additive manufactured sample, especially after the corrosion test. This indicates the formation of a more stable and maybe thicker protective layer on the commercial sample, protecting it more against corrosion, which we could clearly see in the previous results. Here you can see the SEM images of the samples before the corrosion test, with the parameters applied on the SEM instrument depicted here. As you can clearly see, except of a few imperfections here and there, the samples are relatively smooth. Here you can see the SEM images of the samples after the corrosion test, and you can clearly see more damage to the surface. Numerous black dots, which are basically tiny holes in the surface, can clearly be seen. They are known as corrosion pits. You can also clearly see that there are many more of them on the additive manufactured sample compared to the commercial sample. This fits well with the observation that the additive manufactured sample has corroded more than the commercial sample. So to summarize this work, the additive manufactured Inconel 625 samples have a higher corrosion rate than the commercial ones, despite of having the same RA value. For the ICR is the opposite, then the commercial samples have a higher value compared to the additive manufactured ones. The SEM images show a larger degree of pitting corrosion for the additive manufactured samples. This work clearly shows that more optimized production parameters are required to improve the corrosion resistance of bipolar plates produced with this method. I would like to acknowledge the European Space Agency and the Norwegian Space Agency for providing the support and funding for this work. Thank you for your attention.